how do we do that? If we're concerned about the liquidus and solidus, then one way to deal with it is to derive formulas from mu2 equals mu1, the equality of the chemical potentials, that are similar to the ones that we derived before and are in Olander as equation 811, A and B, and which I think you may have derived in homework, but in which we don't assume that gamma I equals 1. So we'll say with the gamma model. So from the homework we had G(A) of the liquid as a function of T minus G(A) of the solid as a function of T divided by RT, which is equal to natural log of XA of the solid and XA of the liquid plus natural log of gamma A of the solid as a function of temperature divided by gamma A of the liquid as a function of temperature, where I've used the property of the natural logarithm to separate out those variables, those terms. And then you do the same sort of thing for B, with all the A's replaced with B's. So I'll say here, same for B. But, right, XAS equals 1 minus XBS, and XAL equals 1 minus XBL. And therefore, we have the two equations. So we would I'm just going to go ahead and substitute these in so as to save time doing algebra. And now I'm going to have to write this out. Sorry. So we're going to call this FA of T, I'm going to define this just for the sake of notation, GAL of T minus GAS of T divided by RT is equal to, minus term, minus natural log of gamma A of the solid divided by gamma A of the liquid, T equals to natural log of 1 minus mole fraction of B in the solid divided by 1 minus mole fraction of B in the liquid. We're going to do the same thing again. Call this F of B as a function of T, and have the B's in here. Wanted to make that equals. Brought this term around to the other side. Minus natural log of X B of the solid as a function of T divided by X B of the liquid as a function of T, which is equal to natural log of X B of the solid divided by X B of the liquid. Okay. Yeah, sorry. Misread that on the chalkboard. Thanks for checking. Thank you. All right. So then what you can do is you can say that E to the FA as a function of T is 1 minus XBS over 1 minus XBL. And you can say that E to the FB as a function of T is equal to XBS over XBL. And then when you combine these together, doing the algebra as we did before, you end up with XBL being equal to 1 minus e to the fa of t divided by e to the fb of t minus e to the fa of t, and xbs is equal to e to the fb of t times the bracket term 1 minus e to the fb of t divided by e to the fb of t minus e to the fa of t, which is quite similar to the alpha and beta equations that we had before. So what do we have here? Again, this is now for non-ideal solutions, where we have the gamma in here. We didn't set that those equal to 1, and so that this term did not drop out. But basically, we just lumped it in with the other functions of t, the Gibbs free energies here, and the RT factor. We lumped that all together and just call it FB instead of beta, and FA instead of alpha, and got something that's somewhat of a similar form. And now we've got an equation that relates composition, now this is in terms of B, but composition of the binary solution as a function of temperature, or if you could flip this around, temperature is a function of composition. But either way, this one gives you the liquidus, because this is the fraction of B in the liquid, and this gives you the solidus, the fraction of B in the solid. And these are for the liquidus and solidus because they were derived from the initial condition that mu of the liquid equaled mu of the solid. The chemical potentials of the two phases were equal, which is the criterion for two-phase equilibrium. All right. Of course, in order to use this equation, right, you still need to know these functions of temperature, including these activity coefficients. Maybe the activity coefficients change as a function of temperature. They probably do. You have to know that in order to be able to make the plot. And then if you wanted to do this the other way, using the excess property model, I'm going to just try to copy this. So from equation 742, and by the way, I'm just going to be dealing with regular solutions, not general non-ideal solutions, just specifically regular non-ideal solutions. So we've got RT natural log of gamma AS is equal to the omega for the solid, XBS squared, and we have the same sort of thing for the liquid, but we have a different omega for the liquid because maybe the interactions are different in the liquid phase, so we just account for that. All right.
Is this Pascal or Oehlinger? Equation. That's Oehlinger.
I don't know. I don't have it written down here. Andrew, can you take a look? See if 742 is this in Oehlinger? Thanks. If it's not, then it's Pascal. I think it's Oehlinger, though.
This is Oehlinger.
Yeah. Okay. So then what we're going to do is we're going to subtract these terms, one from the other. So I'm going to go ahead here and say minus and minus, and add this side, add this side. And then I'm going to factor out the RT. So we're going to get natural log of gamma AS over gamma AL is equal to 1 over RT times the difference in the regular solution terms for the solid first and then the liquid. And likewise, natural log of XBS because that was for A, now this is for B. XBS over XBL, natural log of that ratio is again equal to 1 over RT times omega of the solid, XA of the solid squared minus omega of the liquid, XA of the liquid squared. All right. Interestingly, here for the, when this side is for A, the terms here are in B, and when this side is for B, the terms here are in A.
How did we get that?
We would just do the exact same thing, so this is likewise.
Should the following equation be ln of gammas instead of the x's?
Yeah. And like gamma BS over gamma BL.
Oh, sorry. X's and gammas look a lot alike. Thanks. Yeah, no, it is gamma. Okay. Yeah.
Those omega values, are those for a specific solution, or
Yeah,
are those?
they're not general. It depends on what A and B are. But they don't depend on the composition. So the composition of that binary solution can change back and forth, more A, less A, more B, less B. But that is just for A and B. So then plug in into previous equations. Right, because now we've got these terms here, so I can pop this in for here, this in for wherever it went. And we'll just write it all out, just so that you've got it. This is X. And this is that gamma term. That's for the solid. That's for the liquid. For those of you who are there, that says XBL squared. And then this one is for B. Okay. There we go. So, what does this mean? Well, it's a mess. But what it does is it relates, it's two equations, and it relates composition to temperature. It's going to be terribly difficult to solve these for XBS and XBL. Nevertheless, you can solve these equations numerically to give XBS as a function of temperature and XBL as a function of temperature. Again, remembering here that these compositions, right, this is going to be 1 minus XBL, right, and 1 minus XBS. So basically have two equations and two unknowns. Same deal for those A terms. So it's a mess, but you can do it on a computer. And so then this is a way with the excess property model to plot a binary phase diagram for a non-ideal solution analytically. That is what I wanted to cover right then and there. So that ends that. So what we had covered before was the analytic way to plot binary phase diagrams when the solution was ideal. This completes that concept because now you know how to do it for non-ideal solutions and especially for regular non-ideal solutions. I'm going to leave that now. We're going to talk about phase separation. happens only in non-ideal solutions. It's not going to happen in your ideal solutions. What happens with phase separation is that the attraction between like molecules, that is A and A, or B and B, is stronger than the attraction between dissimilar molecules A and B, below a certain critical temperature. So if the temperature is hot enough, they'll mix fine. But if the temperature is too low, they want to separate out somewhat. Basically, this attraction between the like molecules tends to pull apart the solution into two separate phases. Not that it's not dissolving some of the other one, but